We're designing Uber's ride-sharing platform, a system that connects millions of riders with drivers in real time. It needs to handle ride requests, live location tracking, fare calculation, and payments. At scale, we're talking 10 million daily users, 1 million concurrent rides, with sub-second matching and 99.99% uptime across 100-plus cities worldwide. We begin with the MVP for a single city launch. At the top, we have a mobile app where riders request rides and drivers accept them. This connects to a monolithic web server that handles all business logic, ride requests, driver acceptance, fare calculation, and ride history. The web server stores everything in a PostgreSQL database with tables for riders, drivers, and rides. This simple architecture can comfortably handle 100 to 1,000 rides per day, perfect for validating the concept in one city before scaling. As we scale to 100,000 daily rides across 10 cities, the architecture evolves significantly. We introduce a load balancer to distribute traffic across multiple services. The application tier now splits into specialized services. The WebSocket server handles real-time location updates from drivers and riders, pushing updates with sub-second latency. The matching service is the heart of the system, running geospatial queries to find drivers within 5 kilometers of riders. It queries a PostGIS database optimized for location-based searches. To reduce database load, we add a Redis cache storing hot driver locations, enabling sub-second matching for the most active areas. This architecture handles real-time tracking and intelligent driver-rider matching at scale. At global scale with 1 million concurrent rides, we deploy a full microservices architecture across multiple regions. Mobile apps connect through a CDN for static content and an API gateway that routes requests to the nearest region. The monolith is now broken into specialized microservices. The matching service handles driver-rider pairing with sophisticated algorithms. Trip management tracks ride lifecycle. Payment service integrates with external payment gateways for secure transactions. Notification service sends real-time updates to riders and drivers. Analytics service processes data for surge pricing and demand prediction. All services communicate through Kafka, which streams location events, ride events, and payment events in real time. The data tier uses geosharding to partition data by region, ensuring low latency globally. A distributed cache layer spans regions for hot data. The analytics pipeline processes billions of events daily to optimize pricing and predict demand. This architecture achieves 99.99% availability, handles 1 million concurrent rides, and delivers real-time updates with sub-second latency across 100 cities worldwide. Let's dive deep into the matching service, which is the brain of Uber's platform. This service handles the critical task of pairing riders with drivers in real time. At its core, we have 4 key components working together. The location tracker continuously receives GPS updates from millions of active drivers. The matching algorithm processes these locations to find optimal driver-rider pairs. The surge pricing engine monitors demand patterns to adjust pricing dynamically. And the ETA calculator predicts arrival times based on real-time traffic data. The entire system must operate under strict performance requirements, sub-200 millisecond latency for matching decisions, handling 10,000 matches per second during peak hours, and maintaining 99.99% uptime. Any failure here directly impacts user experience and revenue. The first critical trade-off is choosing the right geospatial indexing structure. We have 3 main options. Quadtree offers dynamic spatial partitioning that adapts to driver density. It's memory efficient and provides fast range queries, but updating the tree as drivers move requires complex rebalancing operations. GeoHash is simpler, encoding locations as strings that work natively with Redis. It enables easy sharding and is straightforward to implement. However, it suffers from edge cases where nearby locations can have very different hash prefixes, and precision is fixed at creation time. S2 geometry, developed by Google, uses a Hilbert curve to map the sphere to a one-dimensional space. It eliminates edge cases entirely and scales to global operations, but requires more complex setup and has a steeper learning curve. Uber chose S2 geometry because global consistency and eliminating edge cases are worth the implementation complexity at their scale. The second major trade-off is choosing between greedy and optimal matching algorithms. The greedy approach uses first-come first-serve logic. When a rider requests a ride, we immediately find the nearest available driver and assign them. This gives us incredibly low latency of just 50 milliseconds and high throughput of 20,000 matches per second. However, driver utilization is only 75% because we're making locally optimal decisions that may be globally suboptimal. The optimal approach uses the Hungarian algorithm to solve the assignment problem. We batch requests over a 5-second window, build a cost matrix considering all riders and drivers, then compute the globally optimal assignment. This achieves 92% driver utilization, significantly better than greedy. But the trade-off is brutal. 5 seconds of latency is unacceptable for user experience, and throughput drops to 15,000 matches per second due to computational complexity. Uber's solution is a hybrid: use greedy matching as the default, but perform local optimization within a 100-meter radius, batching requests in that small area. This gives us the low latency of greedy with better utilization than pure greedy, without the global batching penalty. Location update frequency is a critical trade-off that impacts accuracy, cost, and user experience. Let's compare 3 options. With 1-second updates, we get 95% location accuracy, which is excellent for matching. But the costs are severe: 86 megabytes of data per driver per day, draining 25% of battery per hour, and costing $2 million per month in server infrastructure to process billions of updates. At the other extreme, 10-second updates reduce network usage to just 9 megabytes per day and battery drain to 3% per hour, cutting server costs to $200,000 per month. However, accuracy drops to 72%, which means drivers appear in wrong locations, leading to poor matches and frustrated users. The sweet spot is 4-second updates, giving us 88% accuracy while keeping network usage at 22 megabytes per day, battery drain at 8% per hour, and server costs at $500,000 per month. Uber uses this frequency as a baseline but makes it adaptive. When a driver is moving fast on a highway, increase frequency to maintain accuracy. When stationary or battery is low, decrease frequency to save resources. The geospatial database is the foundation that enables real-time matching at scale. It must handle billions of location updates daily while maintaining millisecond query latency. The architecture uses a 2-tier approach. At the top, we have Redis Geo as an in-memory cache. Redis provides native geospatial commands like geo to store driver locations and georadius to find drivers within a radius. Each Redis node can handle 50,000 operations per second with sub-millisecond latency. Below that, PostgreSQL with the PostGIS extension serves as the persistent store. PostGIS provides powerful spatial functions like st_d within for radius queries and st_distance for calculating distances. It handles about 5,000 queries per second per node, which is slower than Redis but provides durability and complex query capabilities. We use write-through caching. Every location update goes to both Redis and PostgreSQL. Redis serves the hot path for matching queries, while PostgreSQL handles analytics and historical queries. The sharding strategy is geo-based at the city level. San Francisco gets its own shard, New York gets another, London another. Each shard handles about 1 million drivers, keeping query latency low by avoiding cross-shard operations. Choosing the right database technology is critical for geospatial queries. Let's compare 3 options. PostgreSQL with PostGIS extension offers ACID guarantees and supports complex spatial queries like finding drivers within a polygon or calculating optimal routes. It has a mature ecosystem with excellent tooling. However, write performance is limited, it scales vertically rather than horizontally, and query throughput caps at around 5,000 queries per second per node. MongoDB with geospatial indexes provides horizontal scalability and a flexible schema that's great for evolving data models. It can handle 20,000 queries per second and scales out easily. But it uses eventual consistency, which can cause stale location data. Sharding is complex to manage, and it's memory-hungry, requiring significant RAM for indexes. Redis Geo is the speed champion with ultra-fast reads, a simple API using commands like georadius, and throughput of 50,000 queries per second. Perfect for real-time matching. However, it lacks persistence by default. Memory costs are high since everything is in RAM, and it only supports basic radius queries, not complex spatial operations. Uber's solution is a hybrid: use Redis for the hot path where matching queries need sub-millisecond latency, and use PostGIS for persistence and complex analytics queries. This gives us the best of both worlds. Chardaying's strategy determines how we distribute driver location data across multiple database nodes. We have two main approaches. Geo-based Chardaying partitions data by geographic region. San Francisco drivers go to one shard based on latitude 37 point something, New York drivers to another shard at latitude 40, London to latitude 51. This preserves locality, meaning drivers near each other are on the same shard. Radius queries like find drivers within 2 kilometers are fast because they hit only one shard. There are no expensive cross-shard queries. However, hotspot cities like New York or San Francisco get much more traffic than smaller cities, creating uneven load. Some shards are overloaded while others sit idle. Rebalancing requires manual intervention to split busy cities into multiple shards. Hash-based Chardaying uses a hash function on driver ID to distribute data. Driver ID modulo 3 determines which of 3 shards stores that driver. This gives perfectly even distribution and automatic load balancing. The logic is simple. But we lose locality: nearby drivers can be on different shards. Radius queries must hit all shards and merge results, making them slow. For a ride-sharing platform where radius queries are the primary operation, this is a deal-breaker. Uber chose geo-based Chardaying at the city level because preserving locality is critical for fast matching. They handle hotspots by dynamically splitting busy cities into multiple shards when load exceeds thresholds. Replication is critical for scaling read queries, which vastly outnumber writes in a ride-sharing platform. For every location update write, there are dozens of matching queries reading driver locations. We use a master replica architecture. The master node handles all writes, processing 100,000 location updates per second from active drivers. This is the single source of truth. Below the master, we have 3 read replicas. Each replica can handle 50,000 read queries per second, giving us a total read capacity of 150,000 queries per second. This is 3x more than a single master could handle. Replication is asynchronous with about 10 milliseconds of lag. When a driver updates their location, it's written to the master immediately, then propagated to replicas within 10 milliseconds. The key trade-off here is read scalability versus data freshness. With async replication, matching queries might see driver locations that are 10 milliseconds stale. A driver who just moved might still appear at their old location for a brief moment. For ride matching, this is acceptable. A 10 millisecond lag means a driver moving at 60 miles per hour is off by less than 1 meter. The benefit of 3x read capacity far outweighs this tiny staleness. If we used synchronous replication to eliminate lag, write latency would increase from 5 milliseconds to 50 milliseconds, creating a bottleneck that would limit our write throughput. Let's explore how to build an Uber-scale ride-sharing platform on AWS. Here's our complete architecture designed for millions of concurrent rides. Starting at the entry point, riders and drivers connect through our mobile apps powered by API Gateway with Cognito authentication. CloudFront CDN delivers static assets globally with sub-50 ms latency. API Gateway WebSocket endpoints maintain real-time connections for live location updates, while the REST API handles ride requests through an application load balancer. Moving to our matching engine, this is where the magic happens. ECS Fargate runs our core matching service that pairs riders with nearby drivers in under 2 seconds. Lambda functions handle surge pricing calculations and route optimization. The geospatial database uses RDS PostgreSQL with PostGIS extensions for lightning-fast location queries within specific radiuses. ElastiCache Redis cluster provides distributed caching for driver locations, updated every 4 seconds. On the data side, we process millions of events per hour. Kinesis Firehose streams ride data to S3 data lakes, or Athena runs analytics for demand forecasting and heat maps. Aurora PostgreSQL handles transactional data with multi-region replication, while DynamoDB stores ride history for instant retrieval. Payment processing runs on Lambda functions integrated with Stripe, ensuring PCI compliance. Taking a step back, This architecture handles 10 million daily rides with 99.99% uptime. The microservices on EKS with Service Mesh provide independent scaling. Our matching service can scale to 500 instances during peak hours while payment services remain stable. Tools like Clouded.ai can help you design and optimize architectures like this, with built-in best practices for cost analysis and performance tuning. At scale, this infrastructure runs approximately $180,000 monthly, but generates revenue per ride that makes it highly profitable. The key is elastic scaling. You only pay for what you use, and AWS services like Fargate and Lambda scale automatically with demand. We designed Uber from MVP to massive scale. Key decisions: Quadtree with Redis for sub-100 ms driver matching, Kafka for real-time location streaming, and multi-region deployment for global reach. Start with PostgreSQL and basic matching. Add Redis at 10K rides. Deploy Quadtree and Kafka at 100K scale. Go multi-region when expanding globally. Build iteratively, scale strategically.